This is an introduction to Lewis structures for organic and biochemical species. And this video will show the 95% rules. In other words, the rules that will help you get Lewis structures correct 95% of the time for organic and biochemical species. As a quick review from previous courses, we remember that anything in the first column has a valence of 1 and would tend to make one bond. Hydrogen is the only element in the first column that makes covalent bonds on a regular basis. The other elements make ionic bonds, and all the elements here make +1 compounds as ions. In the second column, the valence would be 2. That's only really useful for beryllium. Everything underneath beryllium tends to become an ion with a +2 charge. We skip the transition elements for the simple rules and come over to the next column, which is the boron column. Everything in this column makes 3 bonds, and again, elements below boron, aluminum, gallium, indium, tend to make ionic compounds with a +3 charge. So 1 bond, 2 bonds, 3 bonds. Logically, carbon column makes 4 bonds, nitrogen column somewhat unexpectedly makes 3 bonds, and also has a lone pair left over, and everything in that column tends to make 3 bonds with a lone pair. That's the simple rule that we learned from last semester, the 90% rule. Oxygen, 2 bonds and 2 lone pairs, and the halogen column, 1 bond and 3 lone pairs. Some of these elements, N, O, and F, can also make ions. In that case, it's -1, -2 column, -3 column. The carbon column doesn't tend to make any ions. The noble gases don't tend to make any bonds or any ions, except in very esoteric compounds, which won't be included in the 95% rules for organic and biochemical species. So a schematic of the 90% rules, just to review: hydrogen, very common in biochemistry, makes 1 bond. You need to know that solidly. Boron occasionally will show up. It makes 3 bonds. That's what it looks like. Carbon, extremely common in organic and biochemistry, makes 4 bonds. Nitrogen, phosphorus, arsenic, 3 bonds and 1 lone pair. That's the pattern you should look for. Oxygen, sulfur, selenium, 2 bonds and 2 lone pairs. And the halogens, 1 bond and 3 lone pairs. Simple ions, again reviewing from the 90% rules last semester. Sodium would be a +1. Remember to put it in brackets, and you can either show 8 valence electrons, the underlying valence electrons after the outermost electron in sodium metal is removed, or you can show it with no valence electrons. Chlorine, when it makes an ion, becomes the chloride ion with a -1 charge, and there with all the anions you do show all the valence electrons. So in this case, chlorine started with 7 valence electrons when it was neutral. When it became an ion, it ended up with 8 valence electrons. Back to the periodic table to review one more item from the 99% rules from last semester. Elements in the second row and above cannot violate their octet. They can't ever have more electrons around them in a shared covalent compound than 8 for the second row and 2 for the first row. But elements in the third row and below can have up to 18 electrons around them. The S electrons are 2 from the S's, 6 from the P's, and they have empty d orbitals that they can use to bond. So these elements, third row and below, can violate their octet. That's going to be especially significant for phosphorus, sulfur, arsenic, selenium, and tellurium biochemically. We'll also see it for some of the oxo acids of the halogens. So these still are part of the 95% rules for biochemistry. Phosphorus and arsenic not only have the pattern for nitrogen of 3 bonds and 1 lone pair, but we will see them in very important common compounds having 5 bonds. So that's another pattern you should recognize for phosphorus and arsenic. Phosphoric acid is shown here, H3PO4. As with all oxo acids, the unusual element is in the center. Oxygens are all attached to that, and the hydrogens are bonded to the oxygens on the outside edge. This is a structure you need to memorize, along with all its associated conjugate bases. 1 hydrogen removed, H2PO4, minus, or 2 hydrogens removed, HPO4 2 minus, or all 3 hydrogens removed, the phosphate ion, PO4 3 minus. Sulfuric acid likewise has a different pattern. Sulfur we expect to have 2 bonds and 2 lone pairs like oxygen, but it has an alternative pattern of 6 bonds and no lone pairs. That does violate the octet. There are now 2, 4, 6, 8, 10, 12 electrons around sulfur, but no problem because it's in the third row, just like phosphorus. So you need to know sulfuric acid and its conjugate bases, HSO4 minus and SO4 2 minus. Chlorine, moving over one more column to the right, not surprisingly, you see the pattern here, 5 bonds, 6 bonds, 7 bonds to chlorine. Instead of 1 bond and 3 lone pairs, we see 1, 2, 3, 4, 5, 6, 7 bonds of chlorine in perchloric acid. These are all neutral species. Around the center atom, there's no formal charges. Of course, when you remove the hydrogens, you do get formal charges on the oxygens that are on the outside edge that have lost their hydrogens. While there are other compounds or other Lewis structures you could draw, especially for the ionic species with formal charges on the phosphorus and less than 5 bonds, we will not include those as part of the 95% rules for biochemistry. All the structures that you draw this term should show phosphorus with either 3 bonds and a lone pair, or much more commonly in biochemistry, 5 bonds. Likewise with sulfur. There are other structures that would be acceptable in the sort of the 100%, 99% rules, but for the 95% rules that you're expected to do in biochemistry, we want to see either 2 bonds and 2 lone pairs or 6 bonds for sulfur, unless there's a true reason that you can't do that. Same with the chlorine. Nitrogen hasn't been discussed yet. Nitric acid is a very common oxo acid. It has an unusual Lewis structure where you have to have formal charges to avoid violating the octet on nitrogen. Nitrogen's in the second row, so it cannot violate its octet the way phosphorus, sulfur, and chlorine can. And the consequence is we have 4 bonds to the nitrogen with a plus formal charge, and 1 bond and 3 lone pairs to the oxygen with a minus formal charge. You've seen those before. This has to be the structure for nitric acid and nitrate, and you need to get very used to the idea of nitrogen with 4 bonds and a positive charge, and oxygen with 3 lone pairs, 1 bond, and a negative formal charge. Those are part of the 95% rules for biochemical and organic compounds. And additional exceptions that you'll see, you've actually seen nitrogen with the double bond and 2 single bonds in the previous slide for nitric acid. Nitrogen will also very commonly show up in compounds like NH4+, the ammonium ion, but there are organic versions of that where you put carbons in place of the hydrogens on the outside edge, and then there's more hydrogens out further from that. The essential element that you should focus on is nitrogen with 4 single bonds and a plus formal charge as an ammonium type ion. That should be a pattern that's easy for you to set on paper and recognize. Likewise, the oxonium ion, you've seen that in H3O+, the hydronium ion in previous courses. We will sometimes have carbons or other atoms bonded to the oxygens in place of those H's, but the pattern remains the same, 3 bonds, 1 lone pair, and a positive formal charge as the consequence. And finally, the oxide ion, which you've seen as the hydroxide ion, where there's an H here, can also have carbons and other elements there. But what you need to remember is this pattern that's common in the oxoanions: 3 lone pairs, 1 bond pair, and a formal negative charge as a pattern that's acceptable for oxygen in the 95% rules. That concludes the review of the 90% rules and the introduction to the 95% rules for biochemical and organic species.